Okay, we're back now, and we're going to talk about subsequences, and we're going to see where that subsequence idea takes us. So we finished before our break by pointing out that we said all sequences, in fact, have monotone subsequences, and those monotone subsequences, if they're bounded, they're going to converge according to the monotone convergence theorem. But I put the subsequences in quotation marks because we need to actually define that carefully. So that's what we do right here. So suppose we have a sequence in any set. Of course, we're going to be working here with the real numbers, but in general, other times we'll be working with sequences in other sets. So suppose we have a sequence in some set, capital X, a subsequence of that original sequence. It says here it's the sequence x and k for k equals 1 to infinity for a strictly increasing sequence n sub k of natural numbers. Well, that's a little hard to maybe parse out and see exactly what's going on in that definition. So I think the best way to see it is to do several examples and see how the examples fit this definition. So let's start with an example. And in our first example, let's say xn is just n. So this sequence is 1, 2, 3, 4, and so on. And we could even say, in this case, it's in R infinity. We could actually say it's in N infinity because they're all natural numbers. So that's the sequence. But now let's look at a subsequence. And to have a subsequence, this definition says that in a sense, we start with a strictly increasing sequence in the natural numbers. And we call that nk. So let's say that the terms of the sequence nk, let's say those terms, what do those terms have to be? So this sequence has to be a function that assigns to natural numbers k other natural numbers. So this is going to be a sequence from the natural numbers back into the natural numbers, which is in effect what this says here. It doesn't write that explicitly, but it's implicit here. So let's say n sub k. Let's say n sub k is k squared. So that tells me that nk, where k goes 1 to infinity, is, when k is 1, this is 1. When k is 2, this is 4. When k is 3, this is 9. And this is very much in n infinity. That can't be, it's in R infinity, but the key is that this is a function. This sequence is a function from natural numbers to natural numbers. It's a sequence in the natural numbers. And of course, if this is the case, then x sub nk, in fact, let me just write that as a sequence. Let's just say x sub nk, where k goes 1 to infinity, that is the same sequence because xn was equal to n, so x sub nk is equal to nk, which is k squared. So this one is easy, but it might be so easy that it is obscuring maybe some of what's going on. So let's go to another example where maybe a little bit more is happening and we can sort things out maybe a little better. Let's take another simple example. Let's say that the terms of the sequence xn are just minus 1 to the n. Then the sequence xn is the sequence that starts when n is 1, this is minus 1, so this is a sequence that alternates between minus 1 and 1 as n goes from an odd number to an even number to an odd number to an even number. And so let's see, unlike this sequence here, this one, the terms of the sequence aren't themselves all natural numbers. They are integers, but they're not natural numbers because the negative ones in here aren't natural numbers. And so now let's say if nk is 2k, then the sequence nk is equal to 2, 4, 6, 8, and so on. And the sequence x nk, 1k going 1 to infinity, that is going to be, well, nk is 2. I've got 1 here. When nk is 4, that's the next term of the nk sequence. 4 is the second term. It's the fourth term of the original sequence. Then the next term of the nk sequence is 6. That's out here. That's a 1. And of course, I'm only looking at the even numbered terms of the original sequence when I'm looking at x sub nk. And so this is 1, and it just stays 1, so it's the constant sequence. And let's just point out that this, while it is in R, let's point out that it's actually in the set of integers. And so, of course, this is, again, this is a sequence of natural numbers. So this should be infinity here. This is the natural numbers infinity, just like here, because this is a sequence of natural numbers. This is a sequence in the space where the original sequence lives, because its terms are terms of the original sequence, some of the terms. So this is in C infinity. What if instead nk is 2k minus 1? Then the sequence nk starts when k is 1, this is 1. When k is 2, this is 3. When k is 3, this is 5. One more. When k is 4, this is 7. So now, the sequence nk is the sequence consisting of the odd natural numbers. And so when we go back and look at x nk, where k is going from 1 to infinity, this again is a sequence that contains terms from the original sequence, not like this, containing terms that are natural numbers. This then consists of nk is 1. It's the first term of the original sequence, minus 1. When k is 2, I've got nk equal to 3. That's the second term of this sequence is 3. So x3 is the next term here, and that's minus 1. When k is 3, I think I said k might be 3 here. When k is 2, nk is 3. When k is 3, I'm looking at the third term now of the sequence and of this sequence. When k is 3, this is 5. So that means that I'm looking at 5 as the third term of the nk sequence. And so I'm looking at the fifth term of the original sequence, minus 1. And so 2k minus 1 is always odd. In fact, the sequence of nks is the sequence of odd natural numbers. So I'm picking up the terms of the original sequence that have odd indexes, that have odd numbers, odd numbered terms. So minus 1, minus 1, minus 1, so they're all minus 1, and that's a constant sequence of integers. Constant sequence where this is an alternating back and forth sequence of integers. And this is a constant sequence of integers. And what happens if we say nk is k squared again, like we did up here? So now, if nk is equal to k squared, well, we're right back up here, so I'm not going to rewrite this. Let's just say nk 1 to infinity. Well, I'll write it. It just takes a second. That's 1, 4, 9, 16. A sequence of natural numbers. And here, the sequence x nk, that is going to be, the first term of this sequence is the first term of the original sequence, minus 1. The second term of this sequence is 4, so the second term of this sequence is the fourth term of the original sequence, 1. The third term of this sequence is the ninth term of the original sequence, because the third term of the sequence is when k is 3, and when k is 3, nk is 9. The third term of this sequence is 9, so I'm looking at the ninth term of the original sequence, which of course is minus 1. So the squares alternate odd, even, odd, even, odd 25, even 36. And so that means that we're picking up those terms in the original sequence, minus 1, 1, so odd term, odd term, even term. So, well, I should have put on here that this is dot, 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 which is in, and that's equal to the original sequence. You could say, but wait a minute, that's only some of the terms of the original sequence. It's only the first, the fourth, the ninth, the 16th, and the 25th, and so on, terms of the original sequence. And that is, of course, true, but the actual subsequence is itself a sequence of integers, and it's the same sequence of integers as the original sequence, even though it's a subsequence. That's perfectly okay. So there's just a couple of simple examples to kind of see how how the notion of subsequence works here. Now, of course, a subsequence, and it says it in the definition, a subsequence of the original sequence is itself a sequence, and so it must be, since it's a sequence, it must be a function from the natural numbers into the set X. And of course, that is what's happening here. I just haven't written it explicitly looking like a function. In the lecture notes, that is done. I'm just not doing that here. Here I think it's a little more, it's easier to follow if we do things this way. Here, you will notice that in the first example, I had R playing the role of capital X. This was a sequence. Now, this is R infinity. Definition just says X. But of course, the sequence of things in the set X, the set of sequences is X infinity. So R here is playing the role of X because this is a sequence of real numbers. I could have written it as capital Z because these happen to be integers, and then this would be Z to the infinity, and Z would be playing the role of capital X. Here, I explicitly said we're working with integers, so here Z is playing the role of capital X, and so Z infinity here, we would have capital X infinity for the set of sequences over here. So that's how subsequences work. And let's now note a remark about subsequences. If we have a sequence that, in any norm vector space, actually, that converges to some point in the space x bar, then every subsequence has to converge to that same point as well. I don't know, neither one of these converge, so this isn't a good example here. And conversely, of course, if every subsequence converges to x bar, then the original sequence converges there because the original sequence is, of course, a subsequence of itself. So if every subsequence converges to x bar, then the original sequence does. But the key thing here is that if the sequence converges, then every subsequence has to converge to the same point. Easy to show. Maybe I'll give that as an exercise, although I think it may be a little too easy for an exercise. Equivalent statement, of course, is to take the converse, which says a sequence will not converge if it has any, even one, subsequence that fails to converge, if and only if. So, of course, if the sequence fails to converge, it has a subsequence that fails to converge because, again, the sequence is a subsequence of itself. So if the sequence fails to converge, it itself is a subsequence that fails to converge. But this tells us that if it has any subsequence that fails to converge, then the sequence will fail to converge. And that happens, of course, here because, for example, well, I guess the only, well, here's an example here, I guess. This is a subsequence of the original sequence, and this clearly fails to converge, so that fails to converge, although it's all pretty obvious in this case here. So we could go back to our 5 examples that we had last time, and we could note, for example, in example 2. In example 2, we have a subsequence that converges, the even terms of the original sequence, that converges to 1. We have a sequence that converges to -1, and we could clearly take, oh, sorry, that's not example 2. Example 2 converges to 1. Example 3, for example 3, we have a subsequence, the even terms, which converge to 1, and the odd terms converge to -1. And so there we have subsequences that converge, but we could take the subsequence consisting of the first term, the 4th term, the 9th term, the 16th term, the squares as the subscripts. That would be a sequence that alternates as well as a subsequence. It doesn't converge, and the original sequence doesn't converge. Those aren't very instructive examples because the sequences are a little too obvious and simple. But still, we do have this remark that if we can identify a subsequence that does not converge, we know the original sequence can't converge as well. So let's see now what we can do with all these ideas we've developed about bounded sets, bounded sequences, and the monotone convergence theorem and subsequences. So the first thing we can say is this remark here that says every sequence has a monotone subsequence. We actually said that a little earlier, and here we're making a formal remark. Every sequence of real numbers has a monotone subsequence. Let's actually go back here again to our 5 examples. Let's note that example 1, of course, the sequence itself is monotone, so nothing interesting there. And the same with example 2, it's monotone increasing, so nothing interesting going on there. Example 3 is not monotone, but of course, we've already pointed out a couple of times that it has monotone subsequences. The even terms are monotone increasing, limits 1. The odd terms, monotone decreasing subsequence, converges to -1. Nothing interesting in example 4. Example 5, again, we have monotone weakly increasing subsequence that's always 1, monotone increasing or decreasing, monotone constant subsequence that's 0, constant subsequence is 1. So in both of those cases, example 3 and example 5, where we had sequences that did not converge, we did have monotone sequences that were subsequence. We did have monotone subsequences. So that's what this remark says. Every sequence has a monotone subsequence. I'm going to give that as an exercise to prove. But let me point out here that this seems obvious. It seems absolutely, if you've got a sequence of real numbers, it clearly has to have some subsequence that's monotone. Well, that's true. I'm going to give that as an exercise, and it's not terrifically hard to prove, but what happens in proving it, at least when I sat down to prove it, I mean, I've seen it before, but I wanted to reprove it for the course here. It's a little tricky. You think you've got it proved, and then you think about it a little bit, and you think, whoa, I missed something. It doesn't quite work that way. So it's kind of subtle. I will give this an exercise, and I'll provide 1 or 2 hints as to what you might do to get started and do the proof. And then afterward, I'll give a proof so that even if you have trouble actually getting the proof, or if you think you have a proof and you turn it in and we say, that's not quite actually a proof, because it's a little more subtle than it seems, we'll give an actual proof. But I don't want to prove it here. I want you to try to prove it, because it's a good exercise in seeing how things that seem obvious, when you sit down and you try to write out the actual proof, sometimes the things don't turn out to be quite as straightforward to verify as you think. Okay, so next item here on our agenda is the Bolzano-Weierstrass theorem, a biggie, a big-time theorem in mathematics and for economics. So the Bolzano-Weierstrass theorem says that every bounded sequence has a convergent subsequence. Well, let's back up and see why that might be true. It says every bounded sequence has a convergent subsequence. Well, the reason it's true comes back to what we did a couple of screens ago, where we said actually all sequences have monotone subsequences, and the monotone subsequences that are bounded, the monotone convergence theorem says those subsequences converge. But if the original sequence is bounded, then of course any one of its monotone subsequences is bounded too. So the original sequence is bounded. It has to have a monotone subsequence. That monotone subsequence is bounded, and therefore the monotone convergence theorem says that it converges. So in fact, once we have the remark at the top up here, together with the monotone convergence theorem, those two together make the Bolzano-Weierstrass theorem simple to prove. So the trick is to know the least upper bound, to know that the least upper bound property gives us the monotone convergence theorem. Together with this remark up here, we get the Bolzano-Weierstrass theorem. So the Bolzano-Weierstrass theorem says that every bounded sequence of real numbers has a convergent subsequence. In fact, we can take that and easily, in a kind of a neat little proof, we can take that up to R2, R3, R4. We can take that to Rn directly in a neat little proof that every bounded sequence in Rn has a convergent subsequence. And I'm not going to do that proof, and I probably won't give that as an exercise, but I'll refer you to Simon and Bloom, who give that proof, and it's a real nice proof. So it's something you should absolutely take a look at. So we have the Bolzano-Weierstrass theorem, and that theorem tells us that every bounded sequence in Rn has a convergent subsequence. Okay, so a consequence of that we will prove maybe the next lecture or the one after, when we talk about continuous functions, a consequence of this, a direct and simple consequence of the Bolzano-Weierstrass theorem, is the Weierstrass theorem, which says that a continuous function on a closed and bounded, or sometimes we call it compact, subset of Rn will attain both its maximum and its minimum values on that set, not at some limit that's outside the set. So the Weierstrass theorem, for example, tells us, just to give the first example where you will probably see it in your economics courses, is in your first microeconomics course, where you look at consumer theory and you say, we'll assume that the consumer has a continuous utility function or a continuous preference relation over possible commodity bundles that we can represent with a continuous utility function, a continuous function. And so we put that together with the fact that the consumer's budget set is generally closed and bounded. So the consumer is choosing something from a closed and bounded subset of Rn, and he's choosing it, or she is choosing it, according to a continuous utility function. There will be, according to the Weierstrass theorem, at least one bundle that maximizes the consumer's utility among the available bundles, consumption bundles, in the consumer's budget set. So that's just the first instance where you will see the Weierstrass theorem used. You'll see it used over and over in your economics courses. You'll actually see it used over and over in that first micro course in the fall semester. Okay, one last idea that I think we should put in here to link up some of the ideas we've done, but more to the point, to link with some things you're going to see in subsequent courses. And that is the idea of a sequence being a Cauchy sequence. So here I've gone back to a metric space, but you can think of a norm vector space, or you can think of it as being Rn, or you can think of it even being the real numbers. And in fact, probably thinking of it in terms of the real numbers to start with is the easiest thing to do. But I've written it in this general form because that's where you're going to see it down the road in future courses. So we say a sequence is Cauchy if, and now look down at the universal statement here that defines being a Cauchy sequence. It says that for any epsilon, we can go far enough out in the sequence, that's what n bar is, there exists an n bar far enough out in the sequence that any two subsequent terms, any two terms xm and xn, farther out than n bar in the sequence, will be closer to one another than epsilon. They'll be within epsilon of one another. So if we let epsilon be smaller and smaller, then, because this says this has to work for every epsilon that's positive. So this says that if a sequence is Cauchy, then we can let epsilon get smaller and smaller and smaller, and it will always be the case that we can go far enough out in the sequence, n bar and beyond, so that any two terms farther out will be as close to one another as epsilon. So I'm not going to develop that here. I may give you an exercise where you do an example where this happens and you can show it happens, but we're not going to be actually using Cauchy sequences and the Cauchy property or Cauchy criterion for sequences in this course. But it's clearly very closely linked to the things we are doing because of this theorem that says a sequence in Rn converges if and only if it's Cauchy. So this Cauchy property or criterion gives us a kind of a test or a sufficient condition, actually it's necessary and sufficient, but in particular, a sufficient condition that if we can prove something is Cauchy, then we can prove it converges, even though, and this is the strength of this Cauchy idea, we can prove that it converges if it's Cauchy, even if we can't identify what the limit is that it converges to, because this doesn't say what the limit is. This theorem doesn't tell us the limit of the Cauchy sequence. It just tells us that if we have a sequence that's Cauchy, it converges to some limit. There exists a limit for the sequence. That turns out to be pretty useful because there are situations where we actually can't work with the limit because we don't know what the limit is. And let me just point out kind of in conclusion here that we we said that the completeness axiom for the set of real numbers is that R has the least upper bound property. Well, an alternative statement, an alternative version of that completeness axiom actually is that every Cauchy sequence in R converges. So, of course, the definition up here just says that it gives us a property that tells us whether it's Cauchy. The theorem says sequences in Rn, R as well, converge if they're Cauchy, but you're going to see in subsequent courses spaces, metric spaces, normed vector spaces. You're going to see spaces where Cauchy sequences actually don't converge. Unlike R or Rn, where Cauchy sequences always converge, you're going to see situations where Cauchy sequences don't converge. And it's just the spaces where the Cauchy sequences do converge that are kind of the nicely behaved spaces, like Rn, that are called complete spaces, actually. So that's a bit of a preview. We're not going to do anything with this, except I might give you an exercise to show that some sequence is Cauchy. Beyond that, we're not going to use these ideas in this course, but the ideas that we're developing in the course, they are the foundations for lots of things, but in particular, they're also the foundation for working with complete and incomplete spaces, spaces where Cauchy sequences converge, and spaces where Cauchy sequences fail to converge. So we've done a lot here, and so I think that's it for today. See you all next time.